Okay, so in this video, I'm going to give you a bit of an introduction to Logger Pro. I'm using and how you should use it in the IB Diploma Biology course. I'm using an example of an investigation that we just did in order to try to determine the value of the acceleration due to gravity, the value we call g. So I've just opened Logger Pro. I'm going to make so you can see on the left here, you have a spreadsheet where you can enter your data, and then you also have a graph. I'm just going to make the graph a bit smaller so that, because my data table is going to be relatively big. I start off with only 2 columns. I am going to need more columns soon. My independent variable was the length of a piece of cardboard that I was dropping through a light gate. So I'm just going to, so this is the header cell, and I'm just going to change the name there, and I'm going to call this length. The short name is what the value that's going to appear in the table. I'm also going to call that length. Now the units, I'm going to give the uncertainty and the actual units. Now this is meters because it's a measurement of length, but I'm going to give the uncertainty, and that was measured to the nearest millimeter, which is 1,000th of a meter. So I'm going to get the value plus minus. Now I can do that on an Apple Mac computer by pressing the Alt, the Shift, and the plus key gives me that plus minus symbol. I'm then going to put 0.001 because that is 0.001 meters, is 1 millimeter, is the uncertainty of my length. I then put an M because the unit is in meters. Okay. Now I'm going to need some extra columns because these are going to be time, and I measure the time 3 times. If I click on experiment, data, I can click on new manual column. This is a manual column is just a column that I can manually enter my data into. I'm going to call this column time 2, and you'll see in a second why I'm calling this time 2. The units are going to be, so I measure this to the nearest 100th of a second. So it's plus or minus 0.01 s for seconds. Okay. My first column here is going to be time 1. Okay, and I'm going to make another column again. The reason I'm making so many columns is because time was my dependent variable, and I repeated it 3 times. So for each length of the cardboard strip, I got 3 values for time. Okay, so now there I have my values. So I've now got everything ready that I can input my actual data, which I'm going to do quickly for you. Okay, now you'll see that although this should actually be given to 3 decimal places, if there's a 0 on the end, the program automatically only gives it to 2 decimal places. I can change that by double-clicking on the header, and under options, under decimal places, I can say I want 3 decimal places. Click on there, and it gives it to me now to 3 decimal places. I can now enter my time values. Okay, now again, I am going to, I'm just going to change the number of decimal places again. I want it in all cases to be 2. Okay, now this is my raw data. I've got the different lengths of the piece of cardboard, and I have the different lengths of time that it took for the cardboard to drop through the light gate. Now, I'm going to plot a graph if I was to plot a graph with time on my y-axis and length on my x-axis, I would expect that graph not to be a linear graph. And the reason for that is I would expect that the length is equal to the acceleration multiplied by time squared divided by 2. So I'm going to make 3 new columns in which I'm going to process this data to have time squared divided by 2. So I'm going to add 3 new columns. Now these are going to be what are called calculated columns rather than manual columns. So this is going to be, what shall I call this? Time squared 1. And I can, in this little box here, I can put in the calculation that I need to do in order to get that. So I can say I want it to be time 1. That's going to be squared. I'm going to put in brackets, and the whole thing needs to be divided by 2. Okay, so what it does is it automatically takes time 1, it squares it and divides it by 2. Let me just see why it's not giving the full name, which I've called time squared 1. Okay, maybe if I just call it TS1, it might prefer that. Yep, okay, so I'll do a new column. I'll call this TS2. And this is now going to be time 2 squared. And that's going to be divided by 2. Okay, and then I'm going to do one last column. So it's going to be time squared divided by 2. Okay, so I've now got, in these values, I have my raw data for time. These are now my processed data, which is time squared divided by 2. I'm not going to plot all of these. I'm going to take the mean of these. So I need another calculated column, which is going to be mean TS. I'm going to call it TS over 2 because it's time squared over 2. And now what you would think is that for the expression in order to calculate it, that I could go to functions, statistics, mean, and use that to get the mean of the 3 columns. That won't do that. You can only take the mean of all the values in one column. So I'm going to have to do it a bit manually, where I'm going to take TS1 plus TS2 plus TS3, okay, divided by 3. So that's just a manual way of calculating the mean of those 3 columns. Okay, so now I have my length and I have the mean of my processed data. One thing I am going to have to do is determine a value for my uncertainty of the time squared. Now, what I need to do here is, although there's the uncertainty in the measurement instrument, the biggest uncertainty is the random variation because I got different values each time. For example, in the first row, you can see the first time I did the measurement, the time squared divided by 2 is 0.031, and the last time I did it, it's 0.022. So, and that is far greater than the uncertainty of the measuring instrument. So I need to make another column again. Lots of new columns. Sorry, it's not going to be calculated column. I'm going to do this manually. It's a new manual column, and I'm going to call this this is going to be, uncertainty. Okay, now I'm just going to do this quickly in my head. So basically what I do is I look, well, there's the biggest value, 0.031. The smallest value is 0.022. That's a difference of 0.009. I halve that and round it up. Gives me 0.005. Okay, so I've taken the largest value minus the smallest value, and I've taken half of that. If I do the same here, 0.18 minus 0.0, so that's 0.001. These are very similar again now, so 0.001. This is 0.001, and again 0.001. Okay. Right, so I've now got all the columns I need to make my actual graph. Now my graph tries to work out what I already want plotted on it, but it actually hasn't predicted it quite right. On the x-axis I do want length, so it has plotted that correctly. On the y-axis I want to have my mean times squared divided by 2. Okay, I've just realized I do want to put units in for that because I want my units to appear on the graph. The units are going to be it's going to be meters squared, so I can do m for meters. I need to square, so I can get here a superscript 2 divided by 2. Okay, right, so I want my y-axis to be the times squared divided by 2. So you can see it gives me, mean times squared divided by 2, and it gives me the units, and there's my length. Now you can see my points are all really little down here, so in order to kind of spread them out more on the graph, I can go to auto scale, okay, and that spreads them out nicely along the axis. Okay, it's roughly a straight line, which is what I was hoping for. Now I need to add in my error bars. So I'll start off with my horizontal error bars. Now those horizontal error bars, length is my independent variable, so I determined it myself, and I could measure it to the nearest millimeter. So the uncertainty there is just 0.001. So I can, if I double click on here, under graph options, sorry, where is it? So double click on here, error bar calculations. I want it to be a fixed value, and I want it to be 0.001. So my error bars are representing the uncertainty in the measurement. Okay, you can see they're plotted, and they're really tiny. They're so small they are almost the size of the actual data point. My vertical error bars, I imagine, will end up being a little bit bigger than that. So the error bars associated with the mean, double click on there, error bar calculations, instead of having a fixed value, I'm going to use the data in column uncertainty. Okay, so you can see there's my error bars, and that makes sense because this value here had a much bigger uncertainty. That's this uncertainty of 0.005. Okay, so I now have my graph. I've got my error bars. plotted on it, and I now need to add lines of best fit. Okay, so I am going to first of all add just a linear line of best fit, which I get here, and I'm going to, so this is the expected straight line of best fit. I'm now going to plot on the steepest line of best fit, so I want that to go from the bottom of this error bar to the top of this error bar, and the least steep line of best fit at the top of this error bar to the bottom of this error bar. So I can do that by on here, which is to add a curved fit. I want it to be linear, and I want it to be manual. Now, the values that I've got of the automatic line of best fit had a y-intercept of pretty much 0, so I'm just going to put that on a 0 there, and the slope was 0.0, it's about 0.07, so I'm going to put that as 0.07. So I'm going to get a line of best fit that is pretty close to the data already. Okay, so there it is. Let me just separate these out. Now what I want to do is I want to change the actual position of this manually, so it goes from the bottom of that error bar to the top of that error bar. So if I click on slope, and then what I do is if I move the cursor to the end where I get the little hand, I click there, and what I can do is I can change the slope of it until I get it to about where I want it. The y-intercept I need to change to bring it down a bit. Oh, okay. What's happening here is when I click with a little hand, I'm now using the arrow keys up and down in order to move the line up and down. But what it can happen is that it's moving it up and down too much. So if I double click on this box, I can make the increment for slope, I'll make that a little bit smaller, and also the increment for the y-intercept, I make that a bit smaller. Now, if I click here, oh, it's still a little bit too big. You see it's jumping so far. So I'm going to make an extra 0 in there. Okay, it might still be too much. Let's have a look. Okay, it needs to be a little bit steeper. And it needs to go down a little bit. Okay, again, it's jumping too much, so I'm going to add another 0 in there. Another 0 in there. Now I should be able to adjust it more precisely. Okay, so that's pretty good. Okay, so you can see it's going through the bottom of that error bar, the top of that error bar. Okay, and I'm going to add another manual line of best fit, and it's going to be linear again. Let me just have a look. So the slope needs to be about again 0.0, I'll put 0.06 because I can see that it's going to be a little bit less than the slope of this one. The y-intercept I'm going to put as about -0. I'll just leave it at 0 because that's pretty close. Okay, so there it is. They can get a bit complex, all these different lines. If I move these out the way, it should be easier to view it. Okay, I'm just going to change the precision here again, so that I can adjust them easily. Okay, so I want to change my y-intercept. I want it to be a little bit less. Okay, sorry, I needed to go from the slope. Okay, nearly there. Okay, so you can see I've now got my line of best fit, which is this one here. I've got the slope of it, 0.06983, I've got, so that is the best fit slope. However, also consistent with my data is a line having a slope of 0.0924, because that also fits with my data and the uncertainties in my data. And I've also got a least steep line that has a gradient of 0.054. So what I can then do is say, well, okay, what's the difference between 0.0292? Let me just do that on my calculator quick. Minus 0.054. Okay, so that is a difference of 0.038. Divide that by 2. Okay, so I've got 0.019. So what I could say is that the gradient of this graph is 0.070 plus or minus 0.019. That would be meters squared divided by 2. Okay, and so that would be my conclusion that I could get from this data.